Assalamu alaikum and welcome to lecture number 30. In this lecture we are going to do some few numericals on the last property, that is duality. We are continuing it from the previous lecture, and we are going to start a new topic, a new chapter, that is for Laplace transform. So if you look at here, this is a pulse in time domain, right? So if you have a pulse in time domain, then its Fourier transform will be sinc function. You understand, this is a sinc function. We have done this example or similar examples, right? Similarly, if you have a sinc function in time domain, then in frequency domain we will have a pulse, right, as defined here. So this is the duality relationships. So we can see the pictorial representation for the previous slide. If you look at this one, we have a pulse in time domain, then we have a sinc function in frequency domain. Similarly, if you have a pulse in frequency domain, then it corresponds to sinc function. So you see we have sinc functions in time and frequency domain for the corresponding pulse function, pulse signal in time or frequency. So let's consider some examples. So for example, we are given a signal x of t equals to 2 over 1 plus t square, and we need to find the Fourier transform. So it's a difficult in ordinary way to find it. So let's exploit the property of duality, right? So we have done similar example that x of t equals to for example e power minus 2 t absolute of t. So we have found the Fourier transform for it, and it was 2 over 1 plus omega square, right? So because we have already this one, now if you look at this one, this is similar to the time domain signal where we have to find its frequency domain, right? So it's 2 over 1 plus t square in time domain, and this is 2 over 1 plus omega square in frequency domain. So writing the equation as on the previous slide, so we say okay, let this be, so this x of j omega, okay, so we have x of j omega, and it is equal to 2 over 1 plus omega square, right? So the first step we did, if you recall, it was something like x of jt, and its Fourier transform was equal to, if you see the previous slide, okay, so this starting slide on, so this is equal to basically 2 pi x, right, and you replace t by minus omega. So this is the duality, right? So we have this. Now it's quite simple. We straight away find that if I replace omega by t, so I have x of jt, and this is equal to 2 over 1 plus, so now I will have t square, because I have replaced right, omega by t. So I have this, right? So now because this one equals to this, okay, so from here we get this signal. Now to find the Fourier transform of this is simply scaling the signal by 2 pi and replacing minus omega, right, replacing t by minus omega. So this was your x of t, right? In this case this is your x of t. So what I do, I will just replace, because if I have this, okay, so I can easily find the Fourier of this, right? So that will be straight away scaling by a factor of 2 pi, and the corresponding x of t is this one. So scaling by a factor of 2 pi and replacing t here with minus omega. So because we are taking the absolute of it, so whether we take minus omega or plus omega, absolute will result into same. So that means we'll get e power minus, and this is omega, absolute of omega. So this is the Fourier transform of the signal, and you can see how straightforward it is to find, right? So the next numerical problem we have is this one. We have to find the Fourier transform of this signal, and which is equal to x of t, and it is equal to 1 over 1 plus gt. So that's also a bit tough to do it in a straightforward way, right? So the better option is that we can find it using the duality property. So if you recall, we have similar Fourier transform, right? So that was, for example, if we have x of t equals to e power minus t and u of t. So if you recall, we have done such example, and it has Fourier transform which is equal to 1 over 1 plus j omega, right? So if you look at the two signals, they are quite similar, quite same maybe, with the exception of the independent variable, because in this case we have independent variable as omega, and here we have independent variable as t. So again we can straight away do it, and we say okay, because x of j omega equals to x of j omega equals to, so x of j omega equals to 1 over 1 plus j omega. So that means x of jt equals to 1 over 1 plus gt, right? So exactly what we have. Okay, so its Fourier transform is quite straightforward, and we say it is equal to 2 pi scaling by 2 pi and x of minus omega, is it? So now what was the time domain signal for this signal? So the time domain for this one is basically this one, right? The time domain signal for this one is simply what? E power minus t u of t. So that means here I'll just replace t by minus omega. Okay, so that means the Fourier transform for this will be equal to 2 pi multiplied by x of minus omega. So this is your x of t. So what will be the x of minus omega? X of minus omega will be simply replacing the t by minus omega. So here we have e power t, so it will become e power minus and minus, I think it becomes plus, is it? Right? And u of t, so it will become u of minus omega. So this is the Fourier transform for this signal, right? This is your Fourier transform, and this is your input signal. So exploiting the property of duality, we can very easily find the Fourier transform, right? You have input signal like this, whose Fourier transform you want to find. So if you look at this one, if you recall that you have something like this in frequency domain, and if you look at this one, this is what is the Fourier, it is the Fourier transform of this signal. So that means scaling this signal by 2 pi and replacing t with minus omega, I should get the Fourier transform of this signal. and this is based on the exploiting the duality properties. Okay. So with this we start a new chapter, that is on Laplace transform. Right, if you recall that the response of LTI system with impulse response h of t to a complex exponential input of the form e power st is given by y of t equals to h of s e power st, where h of s was, if you remember, integration from minus infinity up to infinity h of t e power minus st dft. In this equation, st was replaced with j omega, and we said that s is basically purely imaginary. So when s is purely imaginary, then we call this transformation as Fourier transform, right? But s is not normally uh, 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 imaginary, right? Because s equals to sigma plus j omega, right? So you understand, in case of Fourier transform, we took s as purely imaginary and we said s equals to j omega, but in this case s is not purely imaginary and s equals to sigma plus j omega. So in that, if you recall, for the case of the Fourier, we said a system is stable only if its impulse response is absolutely integrable. So in that case, when the response is absolutely integrable, we call such a system as stable system, right? Now in this case, it is not necessary that impulse response must be absolutely integrable. That means the Laplace transform is used for both stable and unstable LTI systems. Laplace transform is particularly useful for the analysis of the feedback systems. So we can write bilateral Laplace transform x of s. If you recall, we for the Fourier we use x of j omega, and you understand why this is x of j omega, because we said s in general, s equals to sigma plus j omega, but in case of Fourier we write this to 0 and we set s equals to j omega. So this was the Fourier. But in case of Laplace, we also consider the real part, so Laplace transform, right? So instead of writing it x of j omega, we will write it x of s, and this is equal to, this is the notation for the Fourier for the Laplace transform, and this is equal to integration from minus infinity up to infinity x of t e power minus st. If you recall, for the Fourier we write as x of j omega, and this is, if you recall, this is equal to integration minus infinity up to infinity x of t, right, multiply by this exponential e power minus j omega t, right? So this is, and dt. So this was the case for the Fourier, right? Because you understand, for Fourier, as we assume to have purely imaginary values, right? Now it will be written as this one. So I hope it's quite straightforward to understand, right? This is called bilateral Laplace transform, because we have from the integration is from minus infinity up to the infinity, right? So this can handle both causal and non-causal signals. In contrast to the bilateral Laplace transform, we also have the special case of this one called unilateral Laplace transform. In case of unilateral Laplace transform, we have summation from 0 up to infinity as the limit of integral, and it can handle only the causal signals, right? Whereas bilateral can handle both causal and non-causal signal, right? One more important term is the ROC, or the region of convergence, right? So the ROC is a set of values of S for which the integral of Laplace transform converges, right? To find x of t from x of s, that is, while doing the inverse Laplace transform, it is necessary to specify the ROC. So we'll talk about it later when we will be doing some numerical examples on Laplace transform. So as I said on the previous slide, that unilateral Laplace transform is a special case of bilateral Laplace transform, and all signals are restricted to be causal. To find x of t from h of s, it is not required to specify the ROC, right? So on the previous slide, we said when we reconstruct the time domain signal from Fourier domain signal, we also need to specify ROC, or region of convergence. But in case of unilateral Laplace transform, we don't need to specify this, because we always assume that it is causal. So the next topic is what is the relationship between Laplace transform and Fourier transform. So I have explained you on the first slide also, and here you can also see that basically this is the Laplace transform, and you integrate it from minus infinity up to infinity, and you multiply it by exponential e power s of t, and where s is complex, right? So if I split it into s into sigma plus j omega, then I can write it like this. And writing it like this is, if I take e power minus sigma t here, so the remaining, this expression is basically the Fourier transform. So if I write the Laplace transform in terms of the Fourier transform, then we say that if we write the Laplace transform in terms of Fourier transform, so we say if we multiply e power minus sigma t with original signal x of t and take the Fourier transform of it, it will be equal to the Laplace transform. Let's have a numerical example on Laplace transform. So first example is that x of t equals to equal to e power minus at u of t, and we need to find the x of s. So s can be cleared from the fact that you are multiplying the signal, or the signal is multiplied with u of t. So that means the resulting signal is basically a causal, and because we assume that a is positive, so that means the resulting signal will be exponentially decaying signal, right? So to find the Laplace transform is represented by x of s. So x of s equals to integration from minus infinity up to infinity, and we have x of t, and the exponential multiplied here is basically minus st and dt, right? So that's quite straightforward, because you have dealt such integration, or you have seen such integration for so many times. So I straight away write it from 0 up to infinity, because you understand that u of t is multiplied with it. So straight away writing it like this, right? So I just write integration from 0 to infinity e power minus at, right, and into the exponential minus st dt. So this is basically, again, I will just take t as common. So if I take t minus t common, so I will be left with, let me take the different color, right? So if I take minus t common, right, so I am left with a and t is common, so this will be minus is taken common, so that means I will get a plus s, and not t, a plus just s, and we need to remove this one also, right? So integration of this is quite straightforward because you have found it so many times. So you have minus t and you have s plus a, this is t not r, right? S plus a, or in fact we can write it okay, so this, and the limit of integration is 0 to infinity, and we have the scaling factor minus s plus a, right? S plus a. So if I put them, let me write here, so that means x of s equals to so putting infinity here will result into minus infinity, and minus infinity is 0, so we have 0 minus 1 because e power 0 will be 1, and this is a, and this is s plus a, so this is equal to, this minus cancels with this one, so this is equal to 1 over s plus a, right? So to find the region of convergence for this signal, we consider only the real part, so that means real of s is how much? Real of, right, because s equals to sigma plus j omega, right? So that means we can say real of s basically is sigma. So sigma is real part of s, and this will converge only when so I write just here region of convergence, okay, ROC, or region of convergence, right? So this will be the value of real of s should be greater than minus a, right? Because s equals to s plus, right? So if you replace here value, you can also write it like this, 1 over, so real is sigma, okay, I write here plus a and plus j omega. I write the real part first followed by the imaginary part, so this will be right, so this is your real part, so real part means that sigma should be, sigma plus a should be equal to or greater than 0. So if sigma plus a equals to 0, that means we have, if you put here, so that means we have just a step function, right? So that means for this signal to converge, then sigma plus a should be greater than 0. So when sigma plus a is greater than 0, that means sigma, which is real part of the s, should be greater than minus a. So for all those values of a for which this relationship holds, this will converge, and we'll plot this on the this complex plane. On the x-axis we have the real part, right, and on the y-axis we have the imaginary part of this signal, okay? So if we look at the first the x-axis, so for all values where sigma is greater than minus a, so for example this is the minus a part, right? In case a is negative, so it will be here, okay? Or in case of it is positive, okay, I leave it to you. Okay, you consider and we'll discuss in the live session, right? So the from here onwards, right, from this dark line here towards this, all for all values it will be convergent, it will converge, whereas from to the left side it will diverge. So this is the region of convergence. So here we plot it, right? So I hope this gives you understanding of how we are going to find the Laplace transform and what is region of convergence, right? So all values where this relationship holds. So all values where this relationship holds are the region where it will converge. Where it doesn't hold, then there it may not converge. So let's take another example. Here we have the anti-causal system signal, and it is, right, you understand it why it is anti-causal, because u of t but u of minus t is multiplied with it. So that means this signal will exist from minus infinity up to 0. For the positive value of the t it will be 0, right? So what will be the Laplace transform of it? So if you calculate the Laplace transform of it, it will be exactly what you had for the previous example, right? Just I write it here. So x of s, and this is equal to integration. So because u of minus t is multiplied here, so that means it cannot go beyond 0. So I straight away write like this, and then you say, okay, this is minus, and then we have e to the power at, right, and multiply by the exponential e power minus st dft, right? So that means because they are multiplied, the bases are same, so power will be added. So again, we can straight away write it like integration minus infinity up to 0. So I'll take just t common here. So n minus 1 is also here, right? Minus 1. So I take t common. So I have uh, minus a and minus s and dft. So if you look at this one, do you think this is exponentially growing signal, the resulting signal, right? What do you think? What it is? Is it exponentially growing or it is exponentially decaying? When it's exponentially growing, definitely it will not converge. So when it will be exponentially growing, that depends on the value of the s, especially the real part of this one, right? So if the real part of the s is smaller than a minus a, in that case it will be exponentially decaying, otherwise it will be exponentially growing. So if you integrate it, you will get right, the upper limit is how much? Upper limit is 0. So 0 minus the lower limit. What is the lower limit? Lower limit is minus infinity, and this is minus, right, minus a minus s, and we have a minus here. So again, if I write it there, it will be x of s, and this is equal to e power 0 is 1, and e power minus infinity is 0, so this is minus 1, right? So this is minus 1 over minus a minus s, right? So if I take minus common, then I'll have a here minus, so this minus cancels with this one, so you get exactly the same expression as you got for the e power minus t at u of t, right? So this means you get a plus s, right? So the region of convergence for this will be real of, right? So I just write ROC equals to real of s, right? And here a is plus a should be less than 0, because if this relationship is satisfied, only then it will be converging, otherwise it will be diverging, right? So it will be from minus infinity to 0. You can only integrate it when this one, right, s plus a, it should be less than 0, right? So that means we have region of convergence equal to real of s should be less than minus a, right? So this is again the complex plane, where on the y-axis we have the imaginary part, on the x-axis we have the real part. So you can again look at this one, because this is the value of minus a. So for all values where real, right, real part, which is sigma, you understand sigma, right? Real part is sigma, and these are the values of the sigma. So values of the sigma should be less than a, because when it is less than a, then summing will result into some negative value, right? So when summing results into negative value, the resulting signal will be exponentially decaying. But for the other values, for these values, maybe here, right? So for that case, it will result into positive value. So that means the because you can see here, for example, if I split it, so it will be something like minus a minus s is basically sigma plus j omega, right? But e power j omega has a unit amplitude, you understand that, right? So that means the contribution for the convergence is the real part, that sigma contributes to the its stability or its summation, or right? So that means if I have something like uh, minus a and then minus sigma, so if this has negative value, which is this has positive value, or this is right, so it will result into some negative value, right? Because if a is so simply we can say that it will converge only when sigma plus a is less than 0, right? So when it is less than 0, in that case you get here e power minus is already there, right? So sigma plus s, if that means if I take negative as common, and this is less than 0, so that means this negative and the resulting negative will result into positive. So we get e power t with positive coefficient, right? So when this is positive coefficient, then at infinity it will be 0. But if we don't meet this condition, in that case at infinity the signal will result into infinity, so thus it will diverge. So it's important or necessary that real of s should be less than minus a, right? Or you can use this expression and you can say, okay, sigma, which is real of s, it should be less than minus a. When this condition is satisfied, this signal is going to converge, right? So where will be the region of convergence? So because we say that real of s should be less than minus a, so for example we have a point here at minus a along the negative axis, so all this region will be region of convergence, right? So for all values where this is met, you understand, for this is the generalized expression for this one. So let's consider the next example where we have two exponential signals, or it's the summation of the two exponential signals, right? So it will be the Fourier transform of it. So let's find the Fourier, not Fourier, in fact Laplace transform, right? So x of s, equals to summation integration from minus infinity up to infinity, and we have x of t e to the power minus st and dft, right? So because it consists of two exponential signals, so let's apply on the individual terms, right? So it will be minus infinity to infinity 3 and e power minus 2t and u of t and e power minus st dt plus, so we have minus here, so okay, let's take minus, and then we have integration minus infinity up to infinity, and this is e power minus t u of t and e power minus st and dft. Okay, so because we have step function multiplied here, and you understand unit step function is 1 only when its argument is equal to or greater than 0. So that means the integration cannot be from minus infinity, it can be from 0, and we can remove this term, right? So straight away u of t signifies that the signal cannot be summed from minus infinity up to infinity. Again, if we look at this one, so you see these two are multiplied, both are exponential, and so their power can be added. So that means we can just write minus st here. Okay, so we can remove this one. Okay, now because t is common, in fact minus t can be taken common, so we have minus 2 plus s, right? So it will be something like minus t is common, so we have 2 plus s, 2 plus s here. Similarly, here again we have the step function multiplied here, which tells that the summation cannot be from minus infinity. In fact, it can be from 0, and again we can take minus t common. You understand, both are exponential, so and multiplied, so the powers can be added. So we take minus t common. When I take minus t common, I'm here left with 1 and plus s, right? So I can remove this term. So that means I have dft here. Okay, so what will be the integration of it? It will be, again, if we talk about the region of convergence, so you see this signal is going from 0 up to infinity, so t has positive value, right? So when t has positive values, that means to make it exponentially decaying, 2 plus s must be greater than 0. If 2 plus s is less than 0, that means negative is there, so that negative and this negative becomes positive, and then you sum it from 0 up to infinity, it will diverge. So for convergence, this one, it is must that we have 2 plus in fact real of s, right? 2 plus real of s should be greater than 0. You understand, when it is equal to 0, what will happen? So you'll have a constant and you have integration from 0 to infinity, so again it will diverge. So that means it is must that 2 plus real of s must be less than greater than 0. So that means real of s, right? Real of s should be greater than minus 2. This is for the first part, right? So okay, I write here minus, and we have 2 plus s, okay, and integration of this. So when I put the upper limit is infinity, so if I put infinity in place of t, then I get my e power minus infinity, and e power minus infinity in fact is 0. Similarly, when I put 0 here, so e power 0 is 1, so I have minus 1. So this minus and this minus become plus, so I have, okay, so no need to write 0 here, so I have just 1 over 2 plus s here, right? And the next term is minus, okay, because we have 3 here, so I have to write 3 here. Okay, again we have minus, and we have 1 plus s. So the similar argument applies, that if 1 plus s is less than 0, in that case that means it will be negative, and this negative and already negative, it will become positive, and when you sum it, then because it becomes positive, it's exponentially growing signal, so at infinity it will diverge. So again, for this part, it is must that real of s plus 1 should be greater than 0, right? So that means real of s should be greater than minus 1. Okay, so again, if I take the integration, so similar, okay, I forgot to write 2 here, there is 2, so it will be 2 over, you understand, integration, and by putting limit, okay, because it will result into 1 plus s. Okay, so in order for both to the region of convergence for both, right? For the first one, we say it should be, for example, this is minus 2, right? So this is your region of convergence for the first one, right? And for the second, you understand, on this axis we have sigma, and on this axis we have j omega, or we can say this is your imaginary part here, and along the x-axis we have the real part, right? So that means in order for both the signals to converge, yes, for the second signal we have the region of convergence, which is something like this. For example, this is minus 1, right? So all this region greater than minus 1 is region of convergence. So what is the overall region of convergence? So overall region of convergence will be this one, right? Greater than minus 1. So ROC for it will be greater than minus 1. And if you simplify it, you get 1 plus s here, okay, and 3 times, in fact, 3 into 1 plus s, and minus 2 into 2 plus s, and at denominator you have s plus 2 plus s and 1 plus s, right? 2 plus s times 1 plus s, right? So on simplification, it will be something like 3 plus 3s and minus 4 and minus 2s, and divided by, if you take the product of it, it will be something like s square, right? S square plus 3s plus 2, right? So this is 2s and this is 3s, so you are left with s, and this is 3 and this is 4, so 3 minus 4 is minus 1, so that means you can just simply write s minus 1 upon s square plus 3s plus 2, right? And the region of convergence, the overall region of convergence for this will be, that is, I just write here ROC, right? Okay, let me write here ROC for this is real of s, right? Real of s must be greater than minus 1. So with this we end the lecture for today. See you in the next lecture. So one more thing, and this is your homework problem, so I hope you should go through it. I want you to go through it and you're provided with the answer, right? So that's all for today.